Okay, so far in your differentiation toolbox, you have power rule, product rule, and quotient rule, but those rules won't allow you to differentiate any function. So we're going to add another rule. In section 3.2, we're looking at the chain rule. And we're able to use the chain rule to differentiate functions that you can think of as being composite functions. So function composed with another function. Remember, I kind of said these functions I like to think of like the Russian nesting dolls. So, for example, if f of x were the square root of x and then g of x were, let's say, x squared minus 4, then f composed with g, right? Remember fogging off. So f composed with g of x, or I like this notation better because you can see which function is the outside function and which is the inside function. So f composed with g of x is the function f of x evaluated at g of x would be the square root of x squared minus 4. And you guys don't know how to differentiate, how to find the derivative of the function, the square root of x squared minus 4 yet. You can't use just power rule. You can't use product rule. You can't use quotient rule, right? So functions that we can think of as a function inside another function, we're going to be using chain rule to find the derivative of. And chain rule says basically you take the derivative of the outside function and you leave the inside one alone, and then you multiply by the derivative of the inside function. So the function up here, y equals to the square root of x squared minus 4, to use chain rule to find the derivative, we would first rewrite this as x squared minus 4 to the 1/2 power, right? The square root is the same as raising to the 1/2 power. So then dy over dx would be the derivative of the outside. So the outside, remember, we're thinking of it as being the square root or the 1/2 power. So that would be 1/2, and then we subtract 1 from the exponent position. So that's now the negative 1/2 power. You leave the inside alone. So x squared minus 4 is still inside here, and then we multiply by the derivative of the inside, which would just be 2x. Okay, and then to rewrite that without the negative exponent, you see that the 2's would cancel. So we would just have x over x squared minus 4 to the 1/2 power. Okay, so this function, it could be, you could multiply this out to be able to just use power rule. You could also rewrite as a product to use, well, you would still have to use chain rule though. But we're going to use, we don't want to have to multiply this out. So to find the derivative of this function, we're going to think of the cubed, right? The exponent of 3 as being the outside function. And then we're going to think of 2x squared plus 5x minus 3 as being the inside function. So the derivative, to find dy over dx, the derivative of the outside, bring the 3 in front, it's now an exponent of 2, when we subtract 1 from the exponent, and then leave the inside alone, and multiply by the derivative of the inside, which is 4x plus 5. Okay, we could multiply that out if we wanted to, if we were trying to get our answer to match something, but we're not. So let's just, there's no negative exponents or complex fractions, so we're just going to leave the derivative as is. Okay, this is a typo. This should be, here, let me fix this. This should be an x. We're just finding h prime of x. Okay. So to find h prime here, first let's rewrite this so that we don't have to use a combination of chain and quotient rule, or quotient and chain rule, let's rewrite this as 4x squared minus x to the negative second power. Okay, so now the outside function is you could think of it as being x to the negative second power. The inside function is 4x squared minus x. So h prime be derivative of the outside, bring the negative 2 out front, subtract 1 from the exponent, leave the inside alone, and then multiply by the derivative of the inside, which would be 8x minus 1. And then let's rewrite this without the negative exponent. So just the 4x squared minus x to the third power will move to the denominator. The negative 2 is still in the numerator, times 8x minus 1. Okay, so now we have this rewritten without any negative exponents. You could distribute the 2 in if you want, you don't have to. Okay. So we can think of the general power rule as being a special case of the chain rule. And when we use in section 3.3 implicit differentiation, I'm going to want you to think about differentiating with a chain rule perspective. So for example, if we have y equals x cubed, we could think of x as being the inside function, and then the x cubed, or the cubed, as being the outside function. So then from the chain rule perspective, y prime would be derivative of the outside, leave the inside alone, times the derivative of the inside, which is the derivative of x, is just 1. So that's just 3x squared, which you guys know from power rule, that's the derivative of x cubed. Okay, so that's thinking about power rule from a chain rule perspective. Okay, so let's find these derivatives. So we have to rewrite this first before we can use chain rule. We don't have to, but it's easier. I think it's easier if you rewrite it. So this is 10 times 3x minus 4 to the 1/5 power. Okay, so we're going to think of 3x minus 4 as the inside function. Okay, 10 is just a constant, and then the 1/5 power is being the outside function. So we'll do 10 times 1/5 for the derivative of the outside, so that's going to be 2. Leave the inside alone, subtracting, so 1/5 minus 1 would be negative 4/5, and then times the derivative of the inside is just 3. And then rewriting this without the negative exponent, we'll have 6 over 3x minus 4 to the 4/5 power. Okay. All right, so y prime, or you could use dy over dx here for the notation. Derivative of the outside, we're going to multiply 3 by 2, the exponent, so we'll have 6. It's now an exponent of 1. Leave the inside alone. Multiply by the derivative of the inside, which is 8x minus 2. You could multiply this out, or you could leave as is. Remember that exponent of 1 doesn't really need to be written. Okay, so now we're going to look at differentiating functions that require a combination of rules. So notice that this is a product of two functions, and I'm going to rewrite the square root of 2x minus 3 as 2x minus 3 to the 1/2 power. So if we're using product rule, because this is a product of two functions, to find dy over dx. Okay, we have, I'm going to call this factor f of x, this factor g of x. Okay, so write down the first factor times the derivative of the second. And here's the issue, or here's where we need to use chain rule. Because to find the derivative of g of x, right, of 2x minus 3 to the 1/2 power, we have to use chain rule. So to find that derivative, I'm going to put that in brackets just to organize my chain rule work. That'll be 1/2 times 2x minus 3 to the negative 1/2 times 2. Don't forget to multiply by the derivative of the inside. Okay, plus the second factor times the derivative of the first, which would be 2x. Okay, so to clean this up now, you can see that the 2's here will cancel. Okay, rewriting without the negative exponent, that'll be x squared plus 1 over 2x minus 3 to the 1/2 power. Plus 2x times 2x minus 3 to the 1/2. Now, common simplification you'll see in the bookwork would be rewriting this as a single fraction, so getting a common denominator. So to get a common denominator here, I'm going to multiply by 2x minus 3 to the 1/2 over itself. So that now this second term will have the same denominator. So now that we have a common denominator, the numerator will be x squared plus 1 and then plus 2x times, now we have the same base, so we can add the exponents. 1/2 plus 1/2 is just 1. So 2x times 2x minus 3. Okay, and then distributing in the 2x, that would be x squared plus 1 plus 4x squared minus 6x. And then last, combining like terms. Okay, and that's our derivative. Okay. All right, so this function can be thought of as a quotient of two other functions. It could also be rewritten to be a product of two functions, okay? And then you could use, so the way it's written here, you would use a combination of quotient and chain rule. And the way it's written here, you would use a combination of product rule and chain rule. But since we just did product rule, let's just use quotient rule and chain rule. Okay, so to find p prime of t, thinking quotient rule, so low d high, right? So low, and I'm going to have this as t squared over t squared minus 49 to the 1/2 power. So low, derivative of the numerator, so times 2t, minus high, right, numerator times the derivative of the denominator, which I have to use chain rule to find the derivative of the denominator, so I'm going to use brackets to organize that. Okay, so inside the brackets is the derivative of the denominator, and then over the denominator squared. Okay, to clean this up a bit, I'm going to pull the 2t out front here. And then I'm going to rewrite this product without the negative exponent. Also noticing that the 2's will cancel. So, oops. So in the numerator of this complex fraction, we'll have t cubed over t squared minus 49 to the 1/2 power. And then that'll just be t squared minus 49 in the denominator. We want to get rid of the complex fraction. So thinking back to like one of our, remember LCM over LCM for when we were looking to simplify complex fractions with inside limits. We're going to multiply by the least common multiple of the denominators of the complex fraction. Well, there's only one complex fraction here. So we're going to multiply by t squared minus 49 to the 1/2 over itself. Okay, remember the division bar is a grouping symbol. So we will be distributing. Okay, and when we distribute to the first product in the numerator, we'll get 2t times t squared minus 49, and then minus t cubed. And the denominator will be t squared minus 49 to the 3/2 power. Okay, so then distributing the 2t. Um, 98t. Okay, so we get t cubed minus 98t over t squared minus 49 to the 3/2 power. Yeah. Okay. So for this guy, there you also have options. You can rewrite in different ways. I don't want to make it too complicated. Actually, the first thing you notice is that inside here, it looks like we can factor an x in the numerator that will cancel with an x in the denominator. So this can actually be written as, I'm going to change this to the 1/4 power. So this can actually be written inside here as 3x minus 5 over x squared. Okay, so the way that's written, we can do chain rule, and then when we multiply by the derivative of the inside, we'll use quotient rule. So I'm just going to do this method. There are a lot of different approaches you can use, and we can talk more about those in class. So you can actually rewrite this function in different ways so that you could use quotient rule, or you could use product rule, but let's do it this way. So derivative of the outside, negative 3/4. Okay, leave the inside alone. Okay, and now times the derivative of the inside. Well, to find the derivative of the inside, we're going to use quotient rule. So low d high minus high d low all over low low. Okay, clean up the numerator bit there. That will be 3x squared minus 6x squared plus 10x remember that if you have a over b raised to the negative first power, that's equal to b over a to the first power. So inside here, I'm going to take the reciprocal. So x squared over 3x minus 5 now to the positive 3/4 power. And then that'll be negative 3x squared plus 10x over x to the 4th. And we could factor out an x in the numerator here. You could do a lot of simplifying here. We're not going to get too crazy. So it'll be negative 3x plus 10 over x cubed. And we'll stop there. We don't have any complex fractions and we don't have any negative exponents. We'll stop. Okay, so that's chain rule and also some examples of chain rule used in combination with some of the other rules that we've already talked about.